Hello everyone, my name is Zhiming Hu. Today, I'm glad to present our work titled Interactive Planning-Based Cognitive Assistance on the Edge. This is a joint work with Maayan Shvo, Allan Jepson, Iqbal Mohomed in Samsung Ed Center, Toronto. So what is cognitive assistance? Cognitive assistance is one of the most exciting applications in AR glasses, such as Google Glass, HoloLens 2. As you can see, there's also an image of HoloLens 2 here. And it is helpful in a myriad of tasks, such as in healthcare education and training, such as it is also a very important tool for remote support. Moreover, it is also enabled a lot of edge applications, such as cooking assistance and fitness coach. The next question is how to build a cognitive assistant. Fortunately, there are lots of existing work such as Gabriel, Jarvis, and Soar that have explored about how to build it. In general, to build a cognitive assistant, we need two major components. The first component is a perception module, which is to determine the current task state. Normally, we could adopt an object detector or a classifier for this module. The second component is the cognitive module, which will generate the next instruction given the current task state and the goal of the task. For this module, we could apply either state machines or a planner to generate the next instructions. Take the fitness demo we built for our middleware paper last year, for example. The perception module will recognize the activities that the user is doing and count the reps for that exercise. And the cognitive module instead will provide the guidelines for the user about the following steps, like it's time to start the next exercise, or it's time for a rest for a few seconds. While most of the existing approaches adopted state machines for the cognitive module, there are several issues with such designs. The main issue is that the state machines need to be predefined beforehand. Therefore, it cannot list all the possible user errors, thus cannot recover from such failure cases as well. Here is a toy example of a cognitive assistance guiding a user to assembly a sandwich. Suppose we define a linear state machine here in the cognitive module. It works fine if the user is following the instructions step by step. For instance, if the assistant detected the lattice in the third step, then it will ask the user to stack a piece of tomato in the fourth step. However, if a user made a random mistake and put a piece of bread instead of tomato on top of the lattice, the state machine will not be able to recover from such failure case. A planner instead could avoid these issues. With a planner, we can always recover from any user errors and provide timely suggestions. This is one of the most important motivation for this paper, because to be practical, we cannot control the errors that the user is going to make, which cannot be handled by state machines. However, there are two main challenges to apply a planner in a cognitive assistance. First, we need to calculate accurate current task state, which may need more than just visual information. Second, the planner is not computationally efficient as state machines. Therefore, we should not call the planner all the time in each step. Here, we have we define a formal planning problem. In general, a planning problem could be encoded with PDDL by defining the domain, the initial state, and the goal state. Here, the stack XY is the action defined in the domain file, and G is the goal state. For this planning problem, if the initial state is that all the ingredients are clear and on the table, one possible solution pi is as follows, which consists of 5 stack operations. As we can see, it's like the first step is stack ham on bread 1, and second step is stack lettuce on ham. To note that the key to get the current task plan is to obtain the accurate current task state. If we cannot get the accurate current task state, the planning results could be totally wrong. This is the same also applies for state machines. If the state machines cannot get the correct current task state, it cannot go to the next state. In our work, we keep track of the current task state by recognizing the actions taken since the beginning. More specifically, we have a classifier that identifies the top object and decides the actions based on the changes of the top object. For instance, if the top object changes from the bread, ham, lettuce, then we will know that a piece of lettuce was put on top of the ham. However, if we see bread, ham, bread in sequence, it could imply either we have stacked a new piece of bread on top of the ham, or we have removed the ham from the bread. For both of the cases, the perception module will have the same sequence of classification results, which is bread, ham, and bread. After detecting such ambiguous cases in our work, we will initiate a dialogue with the user and ask the user to confirm whether he has stacked or unstacked something to be able to get the accurate task state. As mentioned, a planner is very flexible, but it is also computationally more expensive than state machines. Therefore, it is unwise to run the planner again for each step, even if the user is following the instructions. In our work, we propose a hybrid approach, which will only trigger the planner when the user is not following the original plan. If the user is following the original plan, we just return the next step from the existing plan to the user. It's like, so in our work, we will generate a state machines from the initial plan. If the user is following the initial plan, we directly use the state machine to give the next step instruction to the user. If the observed activity is different from the original plan, we will do the replanning and generate a totally new plan. We also measure the runtime at the planner and the classifier on our edge server. As we can see, the planner is still very efficient. We could further reduce the runtime by using a more powerful machine or trade the optimality of the solution for faster runtime. The classifier takes 20 milliseconds for each image, which is also very efficient. So as we can see that it is feasible to run both the planner and the classifier on the edge very efficiently. Here we show a simple demo of our system.
Stack ham 1 bread 1. Unstack tomato 1 bread 1. Unstack lettuce 1 tomato 1. Unstack tomato 1 bread 1. Stack ham 1 bread 1. Stack lettuce 1 ham 1. Stack bread 2 lettuce 1. Stack tomato 1 bread 2. Stack bread 3 tomato 1. Congratulations! The sandwich is completed.
For the future work, first of all, we will aim to provide personalized instructions if we have the behavior models for the users. Second, as we may have multiple cognitive assistance applications on the edge, how to allocate resources to those applications is another important problem. Finally, in our work, we are considering applications that need strictly ordered actions. In the future, we will figure out how to solve the planning problems with partially ordered actions. A possible approach is linear temporal logic. In summary, we have proposed an architecture for cognitive assistance on the edge. We noticed that ambiguous task states are prevalent, and we need to deal with them. Finally, we should combine the planner with state machines to enjoy both the flexibility of the planner and the efficiency of the state machines. Thank you all for listening to my talk. You can reach me with the email address on this page. Now I'm ready to take your questions. Thank you.